Hi, my name is Tori Maxwell, and this is my Organic Chemistry Lab Report number 3. Extraction is when we want to pull a desired organic acid or base from an organic neutral solution. Now, we can do this by polarizing the desired compound. Once we polarize it, we can then add an aqueous solution to the organic solution. The aqueous and organic solutions will separate because they are immiscible. And now the polarized compound will favor the aqueous solution and the nonpolar compounds will favor the organic. This will allow us to release the organic solution and the unfavored molecules and allow us to keep the aqueous solution with our desired product. Washing is a technique that is used to remove an unwanted compound from a solution. For example, we could have a mixture in water. Now, if we know that one of those compounds are more soluble in water than, say, an organic solvent, then we can add an organic solvent to this solution. The one molecule will then dissolve better in the water than in the organic solvent. So the organic solvent and the water are immiscible and therefore they are separated. Now this occurs in a separatory funnel. So then once the two layers are separated, we can then remove the unwanted compound that is dissolved in the water, and then we are left with our wanted compound that is in the organic solvent. So for my mixture, I was giving the three compounds anthracene, piperidine, and oxalic acid. For my initial step, I would dissolve this mixture into H2O due to piperidine and oxalic acid being able to dissolve into the H2O. The anthracene would not, it is insoluble in H2O, and therefore it would settle out. And so I would run this solution through a suction filtration, and the piperidine oxalic acid solution would go through the filter into the flask, and the anthracene would remain in the funnel. Once the solid is dried, I would scrape the anthracene out of the funnel and place into a vial. And now I am only left with two compounds. So for my next two compounds, I have piperidine and oxalic acid in H2O solution. Piperidine is initially soluble or at least miscible in water. So once it's allowed time to settle out, it will float on top of water. So my next step would be placing the solution into a separatory funnel and allowing it to rest until I can see that piperidine has settled out of water and it floats on top. Now, although both of these liquids are colorless, I would be able to see a miscible line at which I would open the funnel and allow the H2O oxalic acid solution to flow out into a flask, and I would cut it off once I see that it has reached the miscible line, and therefore the piperidine liquid remains in the flask and the oxalic acid H2O solution is out. Once the oxalic acid solution and piperidine are separated, I would release the piperidine liquid into a vial, and now I have separated piperidine and anthracene. Now, the oxalic acid is still dissolved in water, but oxalic acid has a boiling point around 365 degrees Celsius, which is unattainable in a lab setting. So I would place this liquid in a round bottom flask and I would attach it to the rotary evaporator. Now, this evaporator would rotate heating the liquid until the water, which boils at 100 degrees Celsius, is able to evaporate off, leaving the solid oxalic acid into the round bottom flask. I would then remove the flask from the rotary evaporator and allow it to cool. Once it has fully cooled, I would scrape the round bottom flask until I can develop the powder solid that oxalic acid is, and I would place that solid into a vial. And now I have fully separated my three compounds. The procedure for the organic synthesis lab begins with measuring out the starting materials. You take roughly half a gram of 2-naphthol and you place it in a round flat bottom flask and you add a stir bead to it. You then add 1 scoop of sodium hydroxide and ethyl alcohol to it. You then swirl it slightly and you set up the reflux system. While it is dissolved, you add 500 microliters of 1-isobutane to the solution. You then place the solution back onto the Bunsen burner with heat and you wait for the reaction to go to completion. Once the reaction has gone to completion, you set up the TLC plate. When performing the TLC procedure, we begin by splitting the capillary tube by heating it over a small flame until the temperature rises enough that we are able to melt the capillary tube and pull it apart. This gives us 2 capillary tubes that we will use to dab our TLC plate with the solution of the product and of the reactant. So we break off the ends of the capillary tube so that there is a small hole on the ends. We then begin by setting up our TLC plate properly by labeling it with a product co-spot with a product and a reactant spot at the bottom of the TLC plate, roughly about 1 centimeter above the bottom. Once we have those spots labeled, we can then take our capillary tubes and dab it into the product solution, and we can dab it in the product and in the co-spot. We then take the other capillary tube and we dab it in the reactant solution and dab it in the co-spot on the TLC plate and in the reactant spot. We then get a jar with our eluent, which is ethyl acetate. We put that ethyl acetate into the jar just slightly around where the dots begin, so roughly about 1 centimeter deep. We place our TLC into the ethyl acetate and close the jar, and there we observe the eluent move up the plate until it's roughly around 1 centimeter below the top of the plate. Once the eluent has gone to the top of the TLC plate, you then remove the plate and you draw a line to where the eluent went. This will be used to calculate the RF values. Once your TLC plate has completed through the eluent, you then place it under a UV light, careful not to look into the light. Then underneath the light, you can see the lanes of the spotting that you have created. You then see spots on the TLC plate and you circle the spots that you see. These spots will then be determined by placing a ruler next to it, and you can see if there was any impurities or contamination in the tube, or if you still have some reactant in your product. And then with the co-spot, you are able to determine which one was the reactant and which one was the product with the relation of the RF values, which are how far that spots have moved up the eluent divided by how much the eluent moved. After the TLC plate, we are then going to proceed to a quenching reaction. You place roughly about 10 grams of ice into a beaker and you pour the solution over the ice and see a precipitate form. You then place this beaker into an ice bath to let the reaction proceed further. Once it has completed, you set up a suction filtration and you pour the solution through the filtration. You will then see that solid is on the top of the funnel and there is a solution in the flask. You allow the solid to continue through the suction filtration until it is dry. Once that has occurred, you shut off the suction and you can then scoop out the solid and put it onto a weighing paper, weigh it, and place it into a vial, and you have your isolated solid. This reaction is 2-butoxynaphthalene. Now, first off, in analyzing this product, we will examine the TLC plates. So initially, this product is a brown crystal, which produces a TLC plate that looks very similar to this. Now, we can see that in this diagram, that the substrate over here produces a high RF value. This means that it is relatively polar, and we can conclude that that is the sodium hydroxide ethyl alcohol solution. Now, the product at the bottom is not very polar, which is very conclusive with the structure that we are given, as it is a cyclic hydrocarbon with 1 oxygen. And this also shows that the product has some reactant in it, meaning that it did not go to completion and there is still some sodium hydroxide ethyl alcohol solution in the product. Another way we can analyze this product to see if it is conclusive with what we should have gotten is by examining the IR spectrum that was given to us and by examining a literature IR spectrum. So I gathered this off of the internet and I will source it here. And this spectrum I have also drawn on what should have happened. So the green lines are what was given to us in an experimental IR spectrum, where my lines are drawn here and here. Those lines are what the internet has shown. So the only difference is that there are 2 lines missing around 1900, and the depth of the lines around 3000. So the depth of the line dictates that it is not as strong, which can be due to the solvent, which will shift the strength and the wavelength that certain molecules are shown. Also, the molecules at 2000, 1800 between 2000 are usually for a carboxylic acid, which our molecule does not have, so it does make sense that it does not have those wavelengths. The IR spectrum that I have also gathered for comparison used a different solvent, and that is why we have gotten different absorption and different wavelengths were shown at certain signals. So our experimental data was missing wavelengths in between 1800 and 2000 roughly. And that was shown in the literature IR spectrum because the solvent used was an ether. So an ether does have that carboxylic acid bond, and that is why it shows that, and it makes sense for our experimental data to not show that bond. Examining this reaction, I have come to the conclusion that this is an SN2 reaction over an SN1, and this has several reasons. Initially, we are using sodium hydroxide as the nucleophile, but as long as it's a strong nucleophile, it's also a strong base, and this indicates more of an SN2 reaction than an SN1 reaction, because SN1 reactions uses strong nucleophiles and weak bases. And although it is also in ethanol, ethanol is a product solvent, but we do add iodobutane later on. And this is an aprotic solvent. And this aprotic solvent is the solvent that attaches to the molecule. And in this case, due to it being an aprotic solvent, this indicates that it's also an SN2 reaction because SN2 reactions use aprotic solvents as SN1 reactions use protic solvents. Another reason for this is that an SN1 reaction, it is strictly due to having a single step occurring. So this happens with a solvent is usually the nucleophile. So it will just attack the compound that we are wanting. Where here we have the NOH attack the H first and remove it off of the oxygen, and then we have the iodobutane lose its iodine and the butane then attaches to the oxygen. I have come up with this small diagram to illustrate the reaction that occurs, and in the bottom corner I display that this is the intermediate step. With the intermediate drawn in the bottom corner, we can then examine that the butane that moves in onto the oxygen as the hydrogen is being removed can easily enter due to minimal steric clashing. If there was significant clashing, then an elimination reaction would occur, and we do not see that in this reaction, and therefore it is a substitution reaction, and I conclude that it is an SN2 reaction.